Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. I'm Dr. Farhad Ali, your instructor for the course Partial Differential Equation. This is your 14th online lecture, which will be uploaded in the 15th week. So this is your second last uh, lecture. This is the second last week. Okay, the coming will be the final week, and maybe you will have uh, your final examination on the 14th of September. Okay, and I hope that this exam will be online. So we have discussed so far the Laplace transform of function. What is Laplace transform? Why Laplace transform? If there are other tools for the solving of differential equations, then some necessary and sufficient conditions, how to apply this, how to find the Laplace transform of some elementary functions, and also uh, we have applied this to the terms that are relative with respect to space or with respect to time. So now uh, we of course, if we apply the Laplace transform just like a log, we apply the log, so there should be t log to bring the transform variable to the original variable. Okay, so similarly we have inverse Laplace transform. If you apply the Laplace transform, you have already observed that t shift to s plan. So then again, um, from s to t, we have to apply the inverse Laplace transform. Okay, so there are some uh, techniques for this, the Laplace transform, and maybe if we have, so we will discuss Laplace transform in the MS class in very detail. Okay, already you have seen that some of the students have presented also the Laplace transform. So you will have already you have observed or you have noticed the properties and the application of Laplace transform. So far we have discussed the various properties of Laplace transform technique and studied the Laplace transform of some simple functions. However, if the Laplace transform technique is to be useful, Laplace transform technique is to be useful in applications, we have to consider the reverse problem too. That is, we have to find the original function f of t, because after applying Laplace, you will have this f of s. So again, we need this to bring it to the original function. So that is f of t. So we know that its Laplace transform f of s. When we know that its Laplace transform is the Laplace transform of f of t is f of s, thus we need it to again to bring it to the original function. Laplace f of t is f of s. So again the Laplace inverse of f of s, we have to reverse of this. Okay, so take the inverse of this. So Laplace inverse. So Laplace inverse of this thing will be cancel Laplace, and Laplace inverse of this thing will bring back the s variable to t variable. Okay, which is the original variable. So here we have some theorem that if Laplace of f of t is f of s. Okay, look at this one. If the Laplace of f of t is f of s, then the Laplace inverse of f of s plus at will be equal to e power minus at. Okay, look at this one. How, what is this in this theorem states that if the Laplace of f of t is f of s, and then you are asked to find the Laplace inverse of f of s plus a is added to this function. So what will be the Laplace inverse of this thing? This will be nothing but just you have to uh, look at this. This will be exponential function of at with negative sign. If this is positive, there should be negative. If this is negative, there should be positive. Okay, e power minus at and the Laplace inverse of f of s, the reverse of this. Okay, so it means e power minus at and again this function, the Laplace inverse of f of st, which is f of t. So the Laplace inverse of f of s plus at will be equal to e power minus at f of t. Now we are going to prove this theorem, this statement. Since the Laplace of f of t is f of s, and we have Laplace inverse of f of s will be equal to f of t. This is quite clear. We already said that the Laplace of t is f of s, then the reverse will be uh, the original function. Laplace inverse of this will be f of t. Recalling the shifting property of Laplace transform, we find that the Laplace of a minus at f of t as as. We have already used the shifting property that if the Laplace of f of t is f of s, then the Laplace of f minus at will be just to uh, e power minus at will be f s minus a. Okay, but this should be um, plus. Okay, if you have this minus t, so that it should be plus. Okay, or this should be if then the Laplace of at, and this is positive, then it should be e power f of s minus a. But if this is e power minus at, so this should minus minus 2 this, so this will be this should be positive. Okay, if this is f minus a. So let me correct this, that this negative sign is plus. Okay, so this is the shifting property. If we have the Laplace of e power a t f of t s, then by shifting property we know that the Laplace of f of t f of s. So if the exponential function is multiplied with a function, so just we will replace s by s minus a. Okay, if there is positive at, if this is negative at, so then it will be f plus f s plus a. Laplace inverse of f of s plus a equal to e power minus at f of t. Okay, you can see here. Sorry, so we have to change this one. This is okay, and we have to change this one. Sorry, this should be positive. So if we apply the Laplace inverse, so you can see the Laplace inverse to the left hand side and also to the right hand side. So you will see Laplace inverse, it will be Laplace inverse and Laplace will cancel each other, and the Laplace inverse of s plus a will be e power minus at dt. Okay, so now just apply Laplace inverse on both sides. Laplace inverse on this side, so Laplace inverse and Laplace will cancel each other, and Laplace inverse of s plus a is equal to e power minus at f of t. So it has been, now you can see e power minus at Laplace inverse of f of st. What is this? This is the Laplace inverse of f of s. So you can see that we have proved this. Now obtain the inverse Laplace transform of the 4 squared minus 3s plus 5 s plus 1 s squared minus 2s plus 2. Okay, so we have to find the Laplace inverse of this function. So how to find the Laplace inverse of this function? Let me denote this function by f of s because it already transformed to s plan. So this is f of s. Now using the partial fraction expansion, we have to use the partial fraction here. Okay, and you can see this how to use partial fraction. A by s plus 1 plus for the quadratic we have bs plus c divided by s square minus 2s plus 2. Okay, so you already use this, so it's not a big deal. You can find this, and just we have to find what is our objective, to find a, b and c. So by simplification I have used a very simple, just like for the okay, intermediate students. Okay, you can see I have compared first s power 0, then s power 1, and s power square, s power 2, and I have found a, b, c as a 12.5, 8.5, and 1.5. You can solve this equation. Okay, we have three unknowns, a, b, c, and three equations. So you can easily solve this equation to find a, b, and c. So now I have already found this one. You can try if you have any problem on this, so you can try yourself. Now I have just put this a, b, c value, and you can see here 12 by 5 is the a value, and we have 1 plus s plus 1, and the b value is 8 by 5, and the c value is 1 by 5. So now the Laplace of this is equal to, because w 12 by 5 is a constant, so we just take it out and we apply Laplace inverse on where there is s. We will apply Laplace inverse on s. Okay, and similarly 8 by 5 is constant, and the Laplace inverse of this, look at this one, I have subtract and add 1. Okay, minus 1 and plus 1. Okay, and you will see why did I because you can see here on the denominator we have s minus 1 square, so it means that s has been replaced by minus 1 by shifting property. So that's why I need also, I have to, if you look back to your shifting property, so s has been replaced by s minus 1. So also we have s on on the numerator and also in the denominator. So this L will also be replaced by s minus 1. So you can see in the denominator we have s minus 1, but in the numerator we only have s. So that's why I have subtract and add plus 1, 1. Okay, add 1, so add and subtract 1. So I just did this far. Okay, similarly you can see here Laplace inverse, because there is no s in the numerator, so no need to add and subtract plus 1 or minus 1. Okay, now further I have to simplify this. 12 by 5 e power minus 80 and plus 8 by 5. You can see here I have just split this one, 8 by 5 into this thing plus 8 by 5 into 1 by s minus 1 square plus 1. You can see here. Okay, and this is comma t to change this to t function. So 8 by 5, and also here you can see I have used also the shifting property here. Okay, that you can see here. If you look at, we have s minus 1. Okay, so by shifting property, by using the above theorem, f of s minus a, so it will be e power at e power t, okay, minus t. So if f of s minus 1, so e power t, okay, and for this one, we have, this is f of s plus a. So by using shifting property, if you look at this theorem, we have, that's why we have mentioned first the theorem, that this one, that the Laplace inverse of f s plus a is equal to e power minus at, and the Laplace inverse of f of s, a will be, this a will be removed, okay, in this will be we will take it out according by using this theorem, e power minus at, and then the Laplace inverse of f of s only. So we will use this theorem here also, okay. And on the first term, you can see on the first term, we have, this is f of s plus 1 instead of a, f of s plus 1. So we will apply that theorem. So this will be taken out, e power 80. Now a is 1, so e power minus 80, e power minus 80. So a is 1, so e power minus t, and then the Laplace inverse of s, that is 1 by s only, okay. Similarly, here you can see, now it is f of s minus a, not s plus a. So now we will take it out, e power minus into minus, minus and 80. So a is minus 1. We have also minus, and also a is minus. So you can see here, if there is minus, we will have e power t by shifting property, and Laplace inverse of s by s square plus 1 square. Okay, by using the above theorem on shifting property, this will be come out. Okay, so now in this one, this is f plus a, but this one is f of s minus a. Okay, so e power minus a t. So minus and a is also negative, so that becomes positive. And Laplace inverse of s by s square plus 1. Similarly, you can see here, okay, e power minus 80, which is also a is minus, so e power t, and Laplace inverse of 1 by s square plus 1. Okay, we have 2 1 by 5. So also we, okay, 8 by 5. Okay, so you can see here, we have Laplace inverse on this one, s minus 1 divided by s minus 1 square plus 1 square, and again 8 by 5 plus 1 by s minus 1 whole square, and also we have this one. So 1 come from this one, 1 by s minus 1 square by plus 1 square, and which will be multiplied by 8 by 5. Okay, so that is 8 by 5 e power 80 Laplace inverse, and now this one, we have f of s minus 1, so e power 8t, 1 by 5 e power t, and Laplace inverse of 1 by square plus 1 square. So now you can see here, w 12 by 5 e power minus t, and Laplace inverse of 1, or this is just 1. Similarly, 8 by 5 and Laplace inverse of s by square plus 1 is cos t. Similarly, 8 by 5, the Laplace inverse of 1 by s square plus 1, omega s square plus omega square. Now omega is 1, so e sine t, and plus 1 by 5 e power t, 1 by square plus 1 square is again sine t. Okay, so you can see here the Laplace inverse of 4 square minus 3 plus 5, s plus 1 square plus x square minus 2s plus 2 is 12 by 5 e power minus t, 8 by 5 e power t cos t, 9 by 5 e power t sin t. So this is the Laplace inverse of this. Okay. So now this is just how to find the Laplace inverse. Now we apply the Laplace solution of ordinary differential equation by using Laplace transform. How to apply the Laplace transform to the partial differential equation. So far we have applied to only the functions. So now we are going to apply to the differential equation, and that is ordinary differential equation. So the Laplace transform technique is one of the powerful tools for solving the physical problems involving ordinary differential equations. So you can see that if you uh, recall your memory that there are the spring constant, okay, the spring uh, we have derived, okay, the differential equations. And so you can see that there are many physical applications of the ordinary differential equations. And if we have a differential equation, ordinary differential equation, so we need to solve it. Okay. So for the solution, we have other tools to solve the differential equation, but especially now uh, we will see that how significantly Laplace transform plays its role to find the solution of the ordinary differential equation in a very simple form, okay, in a closed form solution, exact solution. And when you apply it, it reduces the ODE to an algebraic equations, okay. The method has a particular advantages in finding the solution of initial value problem without finding first the general solution and then using the given initial condition of evaluating the arbitrary constant. Okay, so far if you recall your memory in the ordinary differential equation subject, we will first find the the general solution, that is y is equal to c1 e power t or e power x and c2 e power okay uh, 3x. Okay, if you remember. So this will be our general solution, and then we will apply the conditions to find the constant c1 and c2. But unlike that methods, the Laplace transform, you can see that before the general solutions, it utilizes its initial and boundary condition to find the constant. Okay, so no need to apply to wait for the last general solution. So uh, initially it uses its conditions, and you will see that at the end there will be no constant, arbitrary constant in our final solution. Now we are going to this is example how to apply the Laplace transform on the uh, ordinary differential equation. Okay, you can see this one. This is y double prime, that is d square y by dt square. This will be the function of t. Okay, remember only Laplace is applicable only for the function f of t. Okay, so it should be differentiating with respect to t. So y double dash double prime means d square y by dt square plus 4 dy by dt plus 8y equal to y of t. This y is also function of t and equal to cos 2t. Look at this one. If you recall your memory and you go back to your ordinary differential equation course, so if you have this equation d square y by dt square plus 4 dy by dt plus 8y is equal to cos 2t. So you have to apply this because cos is the uc, comes in the uc function. So you have to find the uc set of this one and undetermined yc plus yp. To solve this equation, you need to okay, by using that procedure, you have to first find the complementary function yc and then yp. And if you recall your memory, you have observed that there are many problems, complications if this function comes in the yc. So you have to multiply this by x and maybe by x square, by x cube. Okay, so Now no need, we don't need, okay, about that the this function is the solution of the YC or not. Okay, you can see now without that problem are investigating those issues, we directly apply the Laplace transform technique. Okay, these are the conditions that when t is 0, the function value is 2, and the first derivative of the function is 1 on t is equal to 0. Okay, so this is the function value. When you find this, when you find the solution means to remove these bar. Okay, so you have to find the function dependent variable y. So once we find the dependent variable y, so when we put t equal to 0, the result will be 2. And when we take the first derivative of this function and then we put t equal to 0, the result will be 1. If it satisfies this, if your solution satisfies these conditions, then your solution will be valid and will be correct. Otherwise, you will have some problem. You have to go back and revise your methods and solution. Okay, so uh, we have just written this in this form because this will be little bit easy for you. Okay, that what does y prime means this thing, y double prime means this thing, y prime means this one, and this is y function of t and cos 2t. Okay, and look at this one. I have written this y0 of t. This is yt. You can see this is yt. So y0 2 and y dash 0 equal to 1. As uh, in the previous lectures, I didn't find that how to apply the Laplace on the derivative. So before I have, because I realized that first I have to explain this, that what will be the derivative, the Laplace of this function of the derivative. Okay, so before to start or to take the Laplace, to apply Laplace on this differential equation or the differential equation, or to solve this differential equation by using Laplace transform technique, first let me discuss that what will be the Laplace of the derivatives. Okay, I will just take this one first. Okay, that the Laplace of d square y dt square equal to this thing. I will explain this also in this lecture after this. Okay, so let me we have to apply Laplace on this one, this one, this one, and this one. You know that what will be the Laplace of y of t, of course y of s, and what will be the Laplace of cos 2t, of course you know this. This is a function, and it will be square plus s square plus 4. Okay, but what will be the Laplace of this? This is new for you. So let me first apply the Laplace transform for because first we will find the Laplace of this, and then will we find the Laplace of the highest derivative. So the Laplace of dy by dt, according to the definition, in this problem I just use the definition for to apply this long process for your understanding. But in the future you will just use the result of this, not this long process. Okay, so this is f of t. Now your f of t is dy by dt. Okay, and this is the Laplace transform definition: 0 to infinity f of t e power minus st dt, or e power minus st f of t dt. So this is your f of t now. Okay, so how to solve this integral now? Okay, we have two terms in the product. So we apply the procedure of by parts. So we solve this integral by parts because you have to decide which will be the first one, which will be the first and which will be the second one, which for which we apply the derivative will be convenient, or for which we apply the integral to take the integral. Okay, so if we take the integral of this one, it will increase, its power will be increased. So it would be better to take the derivative of this. So sorry, if we take the derivative of this, so it will be the power will be increased from dy dt to d square y by dt square. So uh, uh, to be on the safe side, we have to find the integral of this and derivative of this. So the integral of this, we have the integral of this is we have e power minus st. I have already put here 0, but there should be this step. E power minus st, and the integral of this is yt. Okay. Okay, so let me explain this again, that you have to solve this integral. Okay, so how to solve this integral? This will be to integral of this term will be y of t. Okay, at t equal to 0, and e power minus st. So when you have to apply e power minus st y of t, so when we put the upper limit and lower limit, so you will see that by upper limit e power minus infinity, it becomes 0, so it will make all the first term 0. Okay, so the it will be the integral of this, the first term integral of this, it will be y of t, but upper limit, when you apply upper limit and y limit, lower limit, so you will have equal to this equal to 0 minus, you can see here, this is dy by dt. Okay, and the lower limit is t equal to 0. So this is the upper limit, e power minus st dy by dt, and then the lower limit at t is equal to 0. So at t is equal to infinity, the result is 0. Okay, and at t is equal to infinity, at t is equal to infinity, the result is 0, and the lower limit, when you put dy by dt, because e power 0 will be 1, and dy by dt is equal to, at t is equal to 0, plus you will see minus integral, the integral of this is y of t, and the derivative is minus s e power minus st. So s will be, when we apply the limits, okay, so we will take minus to minus plus, and then we have only the Laplace of dy by dt. Using equation 3, okay, using equation 3 we get, this is equation 3, okay. Okay, sorry, this one is, so we have equation 3, okay. So here you can see here, uh, actually this is dy by dt is y dash, okay, y prime, we can write this by y prime, so minus y prime at t is equal to 0 plus s, and Laplace of dy by dt is equal to sy bar s, okay, and minus y of 0. Laplace of dy by dt is actually equal to plus s y bar is minus y0. So you can see this one, and then by the Laplace of d square by dt square y, this is x square y bar is minus sy0 minus y dash 0. So you have to use that the Laplace of dy by dt is uh, this thing, okay. Okay, this is the Laplace inverse of d square y by dt square minus this is the Laplace, sorry, and this is the Laplace of dy by dt. You just here, I have already done this for you in the last of in the last uh, portion of this lecture. You can see here d square by y by dt square plus 4 dy by dt. So the Laplace of this multiply 4 and 8 y is, and Laplace of cos 2t. So you can see here. Okay, look at this one. Okay, this is the Laplace of d square y by dt square up to, and this is the Laplace of dy by dt, okay, and plus 8 bar y s yt, and Laplace of cos 2t is s by s square plus 4. So you can see here I have just simplified this. S square y bar is minus 2s, okay, and you can see here I have just taken a common y bar is, okay, minus 2 is minus 9. Our objective is to find yt actually, and this is y bar s. So y bar s is equal to, just shift this to the right hand side, and 2s plus 9, and we have already s by s square plus 4. So this should be shift to the right hand side. It is in the product form, so it will be divided. Okay, you can see here and see in this one. Okay. So now y bar is equal to this thing. We need to find yt. If you look at your differential equation, um, this is your differential equation. So what we have to do is to find yt. The solution of this differential equation will be to find yt. So now you can see here, we have y bar of s. So what? How to find yt? So just to find the Laplace inverse of the left hand side and the right hand side. The Laplace inverse of this side will be equal to yt. But what will be the Laplace inverse of this side? So first we have to consider, because the Laplace inverse of the left hand side is quite easy. This will give you yt. Laplace inverse of this thing. So we have to simplify this. This is not easy to find the Laplace inverse of the left hand side. Okay. So we need it to simplify this first by partial fraction. You can see here this is the quadratic. So I just s by s square plus 4, s square plus 4 is plus 8. Okay, so you can see the partial fraction. This is the quadratic equation. So a is plus b s square plus 4, and plus cs plus d s square plus 4 is plus 8. So multiply this by s square, both sides by s square plus 4 into s square plus 4 is plus 8. So we have on the left hand side we have just s, and on the right hand side you have this thing. Okay. Now we have to find a, b, c, d. Okay. So first equate the coefficient of s0, that is constant. You can see 8b plus 4d or 2b plus d equal to 0. And s1 we have on the left hand side the s coefficient 1. We have s, so this coefficient is 1, and 8a plus 4b plus 4c. Similarly for s square and s cube. So we have we have A, B, C, four, A, B, C, D, four unknown and four equations. So you can find, solve these equation 6, 7, 8, 9, equation from 6 to 9 for A, B, C, and D. We have, this is your homework. Just verify, okay? You have to find A, B, C, D by proper procedure, okay? You can make a matrix of this, and then you can find by using matrix and elementary row operation, column and row operation, you can find A, B, C, D. Or by eliminating methods, you can find A, which is 1 by 20, B 1 by 5, C minus 1 by 20, and D minus 2 by 5. So now y bar is equal to, this is A 1 by 20, this is B square plus 4. Minus is common, 1 by 20 plus 2 by 5 square plus 4 is plus 8, plus 2 is square plus 4 is plus 9, and 9 square plus 4 is plus 8. Okay, so you can see, and there is no need of the partial friction. I have just write 2 is by this thing and plus 9 by this thing. Okay, so you can see, just simplify this. 1 by 20 into s into s square plus 4 plus 1 by 5 into 1 by s square plus 4 minus 1 by 20. Apply this minus 20 or minus, okay, on this one. So minus 1 by 20 into s by this thing. So I have add and subtract 2, s plus 2 and minus 2 with this s. And look at this one. This, the denominator is actually s plus 2 whole square plus 2 square. Okay. So when you solve this one, you will get this one. So you can see here in the denominator we have s plus 2, and on the right hand, in the numerator we have s. So that's why s has been replaced by s plus 2. So also this s will be replaced by s plus 2. So that's why I have add and subtract 2. Okay. So minus 1 by 20 is plus 2 and minus 2 divided by this thing, and then I have just written this minus 2 by 5 as minus 1 by 5 and 2 by is plus 2 over square. Okay, so there are just a little bit I have used techniques to simplify this. Similarly, you can see for this one we have, because the denominator is same, so this denominator can also be written as in this form. Okay, so this 2 is from this one and this 2 is now here. Okay, 2 into is plus 2 minus 2 is plus 2 minus 2 by this plus 9 by 2. I have just divide and multiply here 2 because I need this is okay. This is now becomes a formula for the Laplace inverse. Before it was nothing, but when we multiply it, divide it, so then you become formula. Okay, and also this become this one and this one become just like shifting property. Okay, so now I have moved, simplify this more. You can see, okay, this one I have just 1 by 20 s by square plus 4, 1 by, again I need to multiply 2 here because this is nothing, no formula now. Okay, so when we multiply 2 here and divide 2 here, so it becomes then formula sine 2t. Okay, minus 1 by 20, I just separate this s plus 2 by this thing and minus into minus plus 2 by 20, 1 by 20 into 2, 1 by 20 in minus into minus plus 1 by 20 and 2 by this thing. Similarly, minus 1 by 5, 2 by this thing, plus 2, s plus 2 by s square plus 2 and minus 2 by 2 s square plus 2 square plus 9 by 2 and 2s plus 2 square 2 square. Now these are now it's now takes the shape of formulae. Now we can apply the Laplace inverse. Before it was not ready to apply the Laplace inverse transform. Okay. Now finally taking the Laplace inverse, of equation 11, we get Laplace inverse of the left hand side and Laplace inverse of the right hand side. 1 by 20 is common, so you can see, okay, just I have taken it out, the Laplace inverse and Laplace inverse of 1 by t. So you can see here, like in this case, when s is plus or minus, when something is plus or minus with the t, so we apply the shifting theorem here, the shifting theorem here, and the shifting theorem here, here the shifting theorem. So you can see here the Laplace inverse of the left hand side is yt, and you can see now that the Laplace inverse, let me minimize this, okay, that you can see uh, the Laplace inverse of s by s square plus 4 is cos 2t plus 1 by 2 into 5, which is 10. 2 by s square plus 4 is sine 2t minus 1 by 20, minus 1 by 20 Laplace inverse. Look at this one. So it's f of s plus 2 e power minus 2t and Laplace inverse of s by s square plus 2 whole square, which is cos 2t. So I have applied here the shifting theorem. Similarly, you can see e power minus 2t sine 2t minus 1 by 5. This one e power 2t sine 2t plus 2 Laplace of, again shifting theory, e power minus 2t sine 2t cos 2t. Sorry, this one 2 e power minus 2t and cos 2t, and minus 2 Laplace inverse of this, so it is sine 2t, and plus 9 by 2 Laplace inverse of uh, e power minus 2t sine 2t. Okay, shifting theorem. So finally, taking the Laplace transform, Laplace inverse of I have taken this already. So you can see 1 by 20 cos 2t, 1 by 10 sine 2t minus 1 by 20 power minus 2t cos 2t. So you can see here the yt, I have just common 1 by 20 power minus 2t. So you will get this thing plus 1 by 20 cos 2t plus 2 sine 2t. Okay, I have taken 1 by 20 e power minus 2t from, you can see, you can take common e power minus 2t. We have this thing, this one, e power minus 2t, e power minus 2t. Okay, so 1 by 20. So the last answer will be 1 by t 120 e power minus 2t. Now 39 cos 2t, because we have 4 cos 2t minus cos 2t. So 39 cos 2t plus 47 sin 2t plus 1 by 20 cos 2t plus 2 sin 2t. Okay, we have minus 4 sin 2t plus sin 2t. So minus 4 sin 2t minus 10, so minus 50 sin, and minus 50 plus 90 and plus 90. So the result will be the last after simplification, we will just get 47 sin 2t. So that is the now this is the solution. Okay, the solution of equation 1, and you can see there is no constant. So here the constant has been used. You can see here, okay, that your constant has been used here. Let me verify this. Okay, you can see here we have y of 0, y dash of 0. So y dash of 0 is equal to 1. I think, what is y dash of 0? The condition that y dash of 0 is equal to 1 and y of 0 is equal to 2. So you can replace this, okay, this y of 0 by 2 minus 2s and y dash of 0 by minus 1. So that's why you have, okay, when you replace this by this one, you can see here, okay, minus 2s. So this is y 0, okay, and this is y dash of 0, which is minus 1. So both the condition have been used here, okay. So when you apply, okay, and you can see here y dash of 0, we have the value of this, which is 1, okay, and y of 0, which is 2. So you can use that condition, okay. So now uh, this is the ordinary differential equation. So now we have the solution of the partial differential equation when the denominator, when the independent variable is more than 1, okay. In the above example, we have only t, the independent variable was only t, but if you have more than one independent variable, okay, so what will be your solution? So a large number of problems in science and engineering involving the solutions of linear partial differential equations, a function of two or more variables may also have a Laplace transform. Suppose x and t are two independent variables, okay. X and t are two independent variables. Consider t as a principal variable and x as a secondary variable. When the Laplace is applied with t as a variable, the PDE is reduced to an ordinary differential equation. Okay, so it means it reduces the partial differential equation to ordinary differential equation. When the Laplace is applied, so it reduces the PDE to ODE. Okay, the T transform U bar XS. Okay, the PDE is reduced to ordinary differential equation of the T transform to U bar XS, where X is the independent variable. The general solution U bar XX of the ODE is then fitted to boundary conditions of the original problem. Finally, the solution UXT is obtained by applying the inverse Laplace transform. Mm, okay, let me okay, remember that in the previous problem, you have to apply it, okay, the conditions. First you can y of 0, so put where there is t, put it equal to 0. So when y of 0 becomes equal to 1, uh, y of 0 conditions, okay, y dash of 0 is 1 and y of 0 is 2, I think. So when you t equal to 0, if it satisfies the above conditions, and then find y dash of t, dy by dt, and then use t equal to 0, okay. So y dash of 0, we have the conditions. If it satisfies that condition, then this solution will be okay. This solution will be correct. If it satisfies this condition, I will, okay, then I will go back to my solution of the partial differential equation. But look at this one. I just, okay, this one. When we put t is equal to 0 and the result is 2 in the equation, so then it's okay. And when you find dy by dt of the solution, the final solution, and we put t equal to 0, the result is 1, so then your solution is okay. Okay, this final solution will be correct. Otherwise, there will be some problem. It doesn't satisfy. If it doesn't satisfy the conditions, okay, y of 0, the result from this will be 2, and y dash, if we find the first derivative of this, and then we put equal to 0, so the result will be 1. So if it does, this equation is okay. Otherwise, you have to revise your procedure. Okay. So now we come to the point, that is how to find the Laplace inverse of the partial differential equations. We have this example. If ux of t, and this will, I hope this will clear the above method, that how to find the Laplace of partial uy. Okay. If u of xt is a function of two variables x and t, proof that, now look at this one, how it becomes partial u by partial t is equal to s u bar xx minus ux0, okay, in the term, because u is the function of xt, okay. So it proves that this is equal to this thing. So by using the definition of Laplace transform, so now you can see if u is the function of xt, so this is not ODE, now it is PDE. Okay, so you can see by using the definition of Laplace transform, partial u by partial t. Now this is your, just like dy by dt in the previous, in the above example. This is dy by dt are um, du by dt are partial u by partial t. Again, you can see here by using the definition of Laplace, partial u by partial t, this is f of t e power minus st dt. So the Laplace of partial u by partial t is equal to, this is now in the above example we have just used the terms, but now I'm going to find it in proper way, okay, in detail. You can see here, this is first integral of this thing. So the integral of this is uxt. Okay, when you find the integral du by dt, so it will be cancelled. Okay, or d will be cancelled with this one. Actually this is d of ut, so dd will be cancelled, and d of uxt, so this d will be cancelled with this one, and just you will have the integral of this is u of xt, and the limits are 0 to infinity, minus integral of this, which is uxt, and derivative of this, which is equal to minus s e power minus st dt. So now you can see upper limit minus lower limit. When you put upper limit, so e power minus infinity is equal to 0, minus lower limit, so e power 0 t is 1, and u power x 0. Okay, this is the result from this one. Minus into minus plus is, and 0 to infinity u of xt e power minus st dt. So what is this actually? This is the Laplace of f of t e power minus st dt, the Laplace of if t. So by definition it is the Laplace of uxt. Okay, and you see that what is the Laplace f of t is f of s. So now it is the Laplace of uxt, so that equal to u bar xs. Okay, just the Laplace of this is u bar xx, or you can write the capital U. Okay, I have just used um, in the start we have just used f of t and capital F of s, but now I have just used without Laplace. The function is the when you use the function of t before Laplace, to apply the Laplace it is u, but when we transform it to s function, s plane, so I just use u bar. Okay, u bar x of x. So actually this is the Laplace of uxt is u bar xx. Okay, so now if you arrange this, okay, arrange this, so we just write first this one, s u bar xs minus u of x0. So actually the Laplace of du by dt or partial u by partial t is s u bar xs and minus u of x0. So this is without Laplace. Okay, here this is t, which is equal to 0. Now to find the Laplace of partial square u, to prove this, that the Laplace of, this is the first derivative, okay, partial u by partial t. Now the Laplace of partial square u by partial t square is equal to s square u bar of xs minus s u x0 minus u dash x0. Okay, when there is no, you can see there is no bar, so it is no, it is without Laplace. Okay, and we have already used this formula here, you can see in the above, but now I am going to prove this. Okay, so you can use the same formula if you have any confusion that how did it come this step, so you can use. Okay, the procedure now I'm going to simplify for you. Okay, like in this one. Okay, yeah, this is the d square y by this s square y bar is minus sy0 minus y dash of 0. How does it come? So now okay, you can okay, these are same. We have just partial square u by partial t square, and here we have d square y by t square. So these are same. Okay, so you can see now I'm going to find the Laplace inverse, the Laplace of partial square u by partial t square. equal to this thing. Okay, I have to prove this. So by definition, using the definition of Laplace transform, Laplace of partial square u by partial t square is 0 to infinity e power minus st f of t, which is partial square u by partial t square dt. Okay, and to find this integral, first I am going to integral of this function as it is, first function, integral of this. So by integration, one power will be vanished. Okay, partial u by partial t and limit are 0 to infinity minus integral of this, which is partial u by partial t, and derivative of this minus s is e power minus st. So now apply the limits. Upper limit 0 and partial u by partial t, I can write this as a ut, partial u by partial t, x and t is 0. The lower limit is 0. Upper limit is being used. The result is this one. Minus the lower limit, this one. Minus into minus plus 0 to infinity e power minus st partial u by partial t. So what does it mean? This is 0 minus ut x0 plus s e power minus st partial u by partial t dt. What does it mean? That the plus is Laplace of this thing, f of t, the Laplace of this, and we have already found the Laplace of this. You can see here the Laplace of partial u by partial t. The Laplace of partial u by partial t is given this thing. This is the Laplace of partial u by partial t. So this is the Laplace of partial u by partial t, which has already been found. So just put here, okay, and okay, apply this s square u bar x's minus su without bar, okay, minus su x0 and minus ut x0. Just I synchronize this. So this is the Laplace of partial square u by partial t square. You can see this in the above example also we have used this one. So this is the result. How did we get this result? Now what will be the Laplace of partial u by partial x? U is the function of xt, but it is differentiating with respect to space variable, partial by partial x of u bar of xx. So by using the definition of Laplace transform, Laplace of partial u by partial x, now this is not t, okay? So how to find the Laplace of when the function is differentiating with respect to space variable x, y, z? So 0 to infinity f of minus st, f of t dt. This is your f of t now. Okay. So as with respect to t, with respect to dt, partial by partial x is constant. So we just take it out, and we have e power minus st uxt dt. So what does it mean by this f of t? If we have e power minus st f of t or f of xt dt, so it is the Laplace of this thing. So this is the Laplace of uxt, yes, and the Laplace of uxt is nothing but u bar xs. Okay, so that's partial u bar by partial x by partial x. This is nothing. Okay, you can see the Laplace of, there should be the Laplace of partial u by partial x is nothing partial u bar. Here we have partial by partial x of uxt, but now we have partial by partial x u bar x is. Just u change to u bar and t change to s. Similarly, we can find that what will be the Laplace of partial square u by partial x square. So we can write this partial square by partial x square u bar xx. This will be the Laplace. Just u will change to u bar and xt, there is xt will change to xs. Okay, and we can prove this. Look at here. Partial square by partial x square u of xt e power minus st dt. So as this is constant, so we take it out. Uxt e power minus st. That is the Laplace definition, the Laplace of ux of t. So u bar xx and partial square by partial x square. So just u change to u bar and xs. Okay. So hence prove this one. So now look at this one. That what will be the Laplace of partial square u of partial x square partial t. So we have x and also t. It is differentiating with respect to space variable but also time. So you can we can use the definition of Laplace transform, that the Laplace of partial square u, the Laplace of partial cube u by partial square x partial t. This is partial x square, okay, partial t is equal to 0 to infinity. This is f of t, partial cube uxt, partial x square partial t e power minus t dt. So as partial cube by partial x square are, sorry, partial square by partial x square are constant with respect to t, so we take it out, and in the integral we have partial u by partial t. Now because it is differentiated with respect to t, so it is variable now. So uh, uh, if we write this partial u by partial t 0 to infinity e power minus t dt, so this is the definition of Laplace transform, and this is nothing but it is the Laplace of this thing, partial u by partial t, which has already been found. We have already been found this thing, which is s u bar xx minus ux of 0. Okay, so multiply this with this thing. So s partial square u bar by partial x square minus partial square u by partial x square at x is equal at t is equal to 0. This is only u, okay, not this one, okay. Just cross this one. This is not. Okay, so now this is the result for this one. Okay, sorry. So you can see that Laplace of partial cube partial cube u by partial x square partial t is equal to this thing. So why I have done this? Because I will use this. I will use this in the coming class. Okay, in the coming lecture, we will apply the Laplace transform to the partial differential equations. Okay, so remember this, try this to recover all these conditions. If you have any problems, so we can discuss. As usual, I'm okay, so I will be available if you want to call me or want to discuss any problem regarding this lecture. So I will be available. Okay, so this is the end of this. I hope you will go through this, and if you have any problem, so again you can contact me. Okay.